those who fall in love with the problem are the ones that will solve it. Shalom, and welcome to Tel Aviv University. My name is Professor Brian Rosen, and I am the head of the Energy Materials Laboratory in the Department of Material Science and Engineering. In our laboratory, we look at how the crystal structure of materials influences their ability to be catalytic. A catalyst is a material which can accelerate the rate of chemical reactions. The catalysts in our laboratory are those that are connected to energy storage, conversion, and the environment. Our laboratory uses material science in order to learn how the exact atomic position and composition of all of the atoms in our crystal affect its ability to accelerate the chemical reaction. We also use chemical engineering in order to design reactors to increase the efficiency of the systems. This is an extremely exciting project where we are interested in the production and cracking of ammonia. Ammonia is one of the most important chemicals known to man. The nitrogen in ammonia is used to make fertilizers. And without these fertilizers, we would not be able to feed the current global population. Ammonia is also important in the energy sector because inside of a single molecule of ammonia, there are 3 hydrogen atoms. Ammonia can be stored as a liquid, and this makes it easy to transport hydrogen from one place to the other. Currently, ammonia is produced using the Haber-Bosch process. The Haber-Bosch process is an extremely energy-intensive and dirty reaction that produces 1.6% of global CO2 emissions.
By decreasing the temperature and pressure of the process creating ammonia, enabled by our catalyst, we significantly reduce the amount of carbon dioxide emits per ton ammonia. In fact, it will be 50 times less than the Haber-Bosch process.
We developed the material in such a way that during ammonia synthesis, these yellow atoms start to agglomerate and form small nanoparticles. By introducing different metals at these yellow atomic sites, we can get nanostructures only a few nanometers large, made up of all the different metals needed in order to give our catalyst its unique kick. In the first part of our project, we will study how the synthesis process influences the crystallographic structure of the catalyst that we receive. We will use powerful X-rays and neutrons in order to learn about how the position and location of individual atoms affects the catalytic performance. We will then take our catalyst and load it into tubular reactors, such as the one that I'm holding here, in order to test for the ability to produce ammonia at record-breaking levels using low power and minimal emissions.
In the second part of our project, we aim to use the same catalyst for cracking ammonia into hydrogen and nitrogen. The hydrogen will be fed inside a fuel cell, which converts the chemical energy to electrical energy. The same happens in combustion engines, but instead of emitting carbon dioxide, it will emit only water. We plan to work with Israeli companies such as Gensel, who has major interest in green ammonia cracking in order to feed the hydrogen inside the fuel cells such as that. In the final part of our project, we want to make scale up. We want to go from the milligrams to the kilograms. In order to do that, we need to go from the milliliter reactor to the liter reactor. The reason we're doing incremental scale up, as you can see here, is because of the mass transfer and heat transfer affects the crystallography and the performances of the catalyst. And we want to make sure that they stay the same for all sizes. אלה שמתאהבים בבעיה הם אלה שממציאים לפתרון. Those who fall in love with the problem are the ones to find the solution. The challenge of energy and the environment is the one that defines our generation. So we must be the ones who fall in love with it.